So that sorts out displacement in circular motion, so angular displacement, which is our theta, angular velocity, but what happens with acceleration? As I say, when we're looking at these motion problems, acceleration is what we're interested in. So acceleration, we're looking at something with a uniform circular motion. So that basically means the particle has a constant angular velocity. Therefore, the size of the linear velocity must also be constant, because we're simply multiplying it by the radius. But interestingly, it's just the size. Here we go. So there's our circle. Because you would think, if the velocity is constant, then the acceleration must be zero. That's what you would logically think. But it's not, because we're changing direction. So that's what I say, the size of the linear velocity is constant, but the direction that it's travelling in is not constant. And that's where the change in velocity happens. It's actually the direction it's travelling in. So particle is moving from A to P with that constant velocity, but if we look at the acceleration, or let's draw it in. First of all, at A it has a tangential velocity of v, but it's going out in that particular direction. When it gets to P, it still has a magnitude of a v, but it's now going in a different direction. So we're playing with vectors here, basically. So the change must be the difference in the finishing point of the two vectors. That red one there. So initially, velocity is going out there, then it's going out here. So the red line must be the change in the velocity. Okay, let's look at that a bit more. Change in velocity. Well, we just said the magnitude is the same. So that angle there, theta, I could use a bit of geometry, because we know the radius is perpendicular to the tangent and so on, and we can show that that angle actually is theta in that triangle. But what's more about that triangle is it must be an isosceles triangle, because the magnitude of those blue lines there, the velocities, are the same. Now, therefore, it's going to be similar to triangle AOP, because it's also an isosceles triangle. It's got theta up the top. Okay. So, using similar sides in our triangles, the change in velocity over AP, because they would be matching sides, would be equal to V over R, which means the change in velocity is V times AP over R. Now, acceleration, we know, is the change in velocity over the change in time. So my acceleration, V times AP over R times the change in time. Okay. But if you think about circular motion, that change in time is basically approaching zero, because as soon as it moves, it's changing direction in an instant. It's just continually changing direction. So we're interested in is, as that change in time approaches zero. Well, as change in time approaches zero, the length of AP, the chord, would be approaching the length of the arc, or vice versa, but basically they'll be close to being the same thing. So I could say arc AP is the same length as the chord AP. Alright, so acceleration, limit, as delta t approaches zero, velocity times arc AP over r times change in time. Now we know distance equals speed times time. So arc AP will be velocity times delta t. Right? Distance, the arc AP, and so on. So let's substitute that in. Arc AP becomes velocity times delta t. We got v squared delta t on r delta t. Well, the delta t's actually cancel, so that change in time approaching zero is no longer a problem, because it's simply v squared on r. And there we get our acceleration, v squared on r, for circular motion. Do not panic, you do not have to derive that. It is okay to quote acceleration as v squared on r, but that's where it comes from. So, in our uniform circular motion, the magnitude is v squared on r. Now the direction, if I was to go back and look at the direction of this vector, it always ends up going towards the centre of the circle. It's always in that direction. So acceleration v squared on r, although if we put it in terms of angular velocity, remember v is equal to r times omega, it becomes r times omega squared. As I say, we're actually interested in the forces. So mass times acceleration, there's that wonderful formula I'm sure we're familiar with, mv squared on r, or if it's in angular terms, mr omega squared. They're the ones we're going to end up using. Particle mass p, constant angular velocity, going around in a circle. It's giving us the parametric coordinates. Basically, it's the parametric coordinates of a circle, because we just say where's its position as it goes around. So similar to projectile motion, breaking it up into horizontal and vertical components. Show that there is an inward radial force of magnitude mr omega squared acting on p. Now, I just said to you, don't panic. They're not going to ask you to derive this. Perhaps what I should have said is, don't panic. They're not going to ask you to derive this the way I just did it, which I think is more interesting because it really gets down to the nuts and bolts. This is how they would expect us to do something. They've given us the hint by breaking it up into its two components. So there's our circle. Point P is there. Our parametrics for x is r cos theta, for y is r sin theta. So we have an x displacement, we have a y displacement. So to get velocities, we differentiate. Remember, theta is changing. Theta is the variable. So I have to do it implicitly. So differentiating cos theta, I'll get minus sine theta, but times d theta dt. But d theta dt was the angular velocity. So I could rewrite that as minus r omega sine theta. Same thing happens over with the y. When I differentiate sine theta implicitly, I'll get cos theta d theta dt, but d theta dt is omega. So we get r omega cos theta. Now it's the acceleration we're interested in. Differentiate again. Cos theta times d theta dt. Oh, d theta dt is omega. I now get minus r omega squared cos theta. Well, hang on a sec. R cos theta, that was displacement. There it is. Circular motion is simple harmonic motion. What we're basically saying is, if you've got something moving in a circle, if you could turn that circle horizontally, so you're just looking in at the circle, what you would see is a particle going backwards and forwards, just like circular motion. If you were just looking at the horizontal displacement of that particle. So yes, it's going around in a circle, but horizontally it's going backwards and forwards, backwards and forwards. Same happens with the y value. It doesn't matter where you look at the circle, because of symmetry, you would always see simple harmonic motion. So that's one of the interesting things about circular motion. It actually is simple harmonic motion. Alright, I have my two components for acceleration. Let's draw up a triangle so we can work out the overall acceleration. So you use a bit of Pythagoras, and we end up with omega to the power of 4 x squared plus y squared, but x squared plus y squared, our circle is equal to r squared. So there it is. Acceleration is r omega squared. So should they ever ask us to do something, that's how I would approach it. I would start with the parametrics, start with the displacement, and then you can show that r omega squared. Remember, it did say show there was an inward radial force. In other words, that is directed towards the centre. I've got to find this angle here. What's alpha? What's the direction? Okay. Oh, sorry. Force is mass, so there's our force, mr omega squared. Okay, so that angle would be the y acceleration over the x acceleration, the inverse tan of that. So let's sub in. We just said y double dot was minus omega squared y. X double dot minus omega squared x. The minus omega squareds cancel. So in fact, it is the same direction as the displacements. In other words, it's going towards the centre, because the angle is going to be the same as this little triangle here, y over x, which is always going to be that angle theta there, the inverse tan. Alright, let's have a look at one of these satellites in a little bit more detail. Gravitational force is now not just simply G, it's going to be AM on R squared. A is some constant. We're going to show that the radius is the cube root of A on omega squared by considering all the other forces. Well, let's think about it. There is our satellite. What forces are acting on it? Well, I'm going to say the resultant force is going down. When we're dealing with circular motion, the resultant force is what we call the centripetal force, mr omega squared. So yes, it's the resultant, but it'll always be mr omega squared in circular motion. If I'm talking about a satellite going around the Earth, it's directed towards the centre, which would be the centre of the Earth. So that's why I've placed it down. It's going down towards the centre of the Earth. The other forces, well, there it is. There's the force due to gravity. I don't think we're going to worry about resistance in this problem. Would there be any resistance? So the satellite's out in space. I think it's fair to neglect resistance in this problem. So there is only one force. So therefore our resultant force must equal, now notice they're in the same direction this time, so it's not negative. So it's AM on R squared. All we've got to do now is make R the subject of this. Oh, sorry, this one. Divide by M, rearrange. R cubed is A on omega squared. So the radius is the cube root of A on omega squared. Okay. We've got a string. Imagine a string. Wish I had a yo-yo. Now I could actually... Anyway. 50 centimetres long our string is. And we know it'll break if we hang a mass of 40 kilograms or more on it. So we're only going to attach a mass of 2 kilograms on it. So if I just hang it there, it'll hang quite nicely. However, if I start revolving it in a circle, I go crazy. I want to spin around my head and go, yeah, watch this thing spin. How fast can I do it before that string breaks, is the question. Okay. There it is, hanging from the string. What do we know? The resultant force, well, I'm going to point it down. So that's going to be my resultant. What forces do I have? I have gravity. Time to introduce a new force, a thing called tension. Whenever you have a string attached to something, there will always be a force going away from the object up what it is being attached to. So this thing called tension. That's the opposing force. That's the resistive force, if you like. So we know our resultant force is equal to mg minus t. Sub in the numbers. Well, it's just hanging there. Nothing's happening. So I know the result of this is 0. It's just hanging there. So 0 must equal mg minus t. So in fact, yes, this must be balanced. Subbing in the numbers we know for mass, and we're assuming 9.8 for gravity, we get 392 newtons. We know this string can handle a force of 392 newtons, but now we're changing the problem. Instead of just hanging here, we're going to spin it in a circle. Still the same string, but we know it can only handle 392 newtons. So now it's going horizontally around us. What forces do we have? Well, it's now circular motion. So the resultant force is going towards the centre of that circle I'm spinning it in. Tension goes up the string, away from the object. Gravity has no part in this problem because I'm doing a nice horizontal circle. So in this case, the tension will equal the resultant force. Well, we know how much it can handle. It can handle 392 newtons. So let's sub that in. The mass hasn't changed. The radius or the length of the string hasn't changed. But now we know what sort of speed it can handle. So we end up with 2 root 98 radians per second I can spin it at before the string will break. That will do us for now.